On the morning of June 30th, 1908, the sky above the remote Podkamennaya Tunguska River tore open. A blinding flash, brighter than the sun, illuminated the Siberian taiga, followed by a shockwave of incomprehensible violence. 80 million trees were instantly flattened across 2,000 square kilometers of dense forest. It was an explosion estimated to be 1,000 times more powerful than the atomic bomb dropped on Hiroshima. Yet, when the dust settled, the most terrifying aspect of the Tunguska event was not the destruction itself. It was the absolute, deafening absence of the object that caused it. Eyewitnesses hundreds of kilometers away reported a column of blue light moving across the sky, followed by a deafening roar that shattered windows and knocked people off their feet. Seismic stations across Eurasia registered massive tremors. Atmospheric pressure waves were detected as far away as Great Britain. The sheer scale of the devastation suggested a cataclysmic cosmic impact, the kind of event that leaves a permanent, gaping scar on the face of the Earth. But the Siberian wilderness held a baffling secret. There was no impact crater. There were no massive chunks of alien rock buried in the scorched Earth. The celestial intruder had simply vanished, leaving behind a forensic puzzle that would confound scientists for over a century. This was the genesis of Siberia's great cosmic mystery. It defied every established model of planetary strikes, forcing a radical rethinking of what happens when the heavens collide with our world. For almost 2 decades, the site remained untouched by scientific scrutiny. The harsh Russian winters, political upheaval, and the sheer remoteness of the region kept investigators at bay. It was not until 1927 that Russian mineralogist Leonid Kulik led the first official expedition into the heart of the devastation. Kulik expected to find a massive depression filled with meteoric iron, a lucrative discovery for the young Soviet state. Instead, he walked into a nightmare landscape that offered more questions than answers. As Kulik's team approached the epicenter, they observed a chilling pattern. The flattened trees pointed radially outward, perfectly marking the blast wave's trajectory. Yet, at the very center of the devastation, a ghostly grove of trees remained standing. Their branches and bark had been completely stripped away by the intense heat and pressure, leaving them looking like a forest of blackened telegraph poles. This peculiar formation directly contradicted the mechanics of a traditional ground impact. The standing trees suggested the explosion did not occur on the ground. The blast wave had traveled vertically downward before radiating outward, sparing the trunks directly beneath it. This observation birthed the asteroid-airburst theory. The hypothesis proposed that a massive space rock, perhaps 50 to 100 meters across, entered Earth's atmosphere at a staggering velocity. The immense friction and pressure caused the object to detonate catastrophically several kilometers above the surface. An airburst explained the widespread, radial destruction and the standing epicenter, but the paradox's shadow still loomed. If a stony or metallic asteroid exploded with such ferocity, it should have showered the landscape with thousands of fragments. Kulik spent years draining bogs and drilling into the permafrost, searching for any trace of the cosmic bullet. He found nothing. The complete absence of macroscopic debris remained a glaring hole in the airburst narrative. This lack of physical evidence pushed researchers to consider alternative celestial bodies. In the 1930s, British astronomer F.J.W. Whipple proposed that the Tunguska object was not an asteroid, but a small comet. Comets are essentially dirty snowballs, composed primarily of ice and dust. A comet entering the atmosphere would vaporize entirely during a high-altitude detonation, leaving no rocky fragments behind to form a crater. The comet theory gained traction because it elegantly addressed the missing debris. It also offered an explanation for a strange phenomenon observed immediately after the blast. For several nights following the explosion, the skies over Asia and Europe glowed with an eerie, silvery light. Newspapers in London reported that it was bright enough to read by at midnight. Proponents of the comet hypothesis argued that the object's vaporized tail had been injected into the upper atmosphere, reflecting sunlight long after dusk. Yet the comet theory was not without its flaws. Modern computer simulations suggested that a fragile comet would likely disintegrate far too high in the atmosphere to cause the specific pattern of destruction observed on the ground. The energy required to snap 80 million trees demanded an object with greater structural integrity, something capable of penetrating deeper into the lower atmosphere before detonating. The scientific pendulum swung back toward a stony asteroid, but the missing fragments continued to haunt researchers. The breakthrough required looking closer, far beyond what the naked eye could see. Decades later, expeditions equipped with advanced microscopic analysis examined the resin of the surviving trees and the peat bogs surrounding the epicenter. They discovered something Kulik could never have seen. Embedded in the landscape were microscopic spherules of silicate and magnetite. These tiny particles contained high concentrations of nickel and iridium, elements abundant in meteorites but rare on the surface of the Earth. The discovery of these extraterrestrial spherules provided the smoking gun. It confirmed that a cosmic body had indeed vaporized above Siberia. The object had been pulverized into dust, raining down invisibly over the devastated taiga. The asteroid airburst theory was solidified, transforming the Tunguska event from an inexplicable anomaly into a terrifying demonstration of atmospheric physics. Understanding the mechanics of the blast only amplified its terrifying implications. The 1908 explosion occurred over an uninhabited wilderness, resulting in remarkably few casualties. But the rotation of the Earth dictates a chilling reality. Had the object arrived just 4 hours and 47 minutes later, the airburst would have detonated directly over St. Petersburg, the capital of the Russian Empire. The city and its millions of inhabitants would have been instantly eradicated. This realization shifted the paradigm of planetary defense. Tunguska was no longer just an isolated historical curiosity. It became the baseline metric for modern asteroid threat assessment. It demonstrated that an object does not need to be massive enough to create a crater to inflict catastrophic damage. The atmosphere, normally our shield against cosmic debris, could act as an anvil, amplifying the destructive force of a mid-air detonation. The lessons from that ancient site never faded, but they remained theoretical for over a century. Then, on February 15, 2013, the sky over Chelyabinsk, Russia, provided a terrifying modern parallel. A 20-meter near-Earth asteroid entered the atmosphere and exploded nearly 30 kilometers above the ground. The resulting shockwave blew out windows across the city, injuring over 1,000 people. The Chelyabinsk meteor was a fraction of the size of the Tunguska object, yet it served as a visceral reminder of our vulnerability. It validated the computer models built on the Siberian data. Scientists could finally observe an airburst in real time, complete with dashcam footage and satellite telemetry. The physics of the 1908 event were playing out again, proving that these atmospheric detonations are a recurring feature of our solar system's mechanics. Even with modern validation, the original Siberian site refuses to surrender all its secrets. In 2007, a team of Italian researchers proposed a new twist to the century-old investigation. They pointed to Lake Cheko, a small, bowl-shaped body of water located just 8 kilometers from the blast epicenter. The team argued that its unusual conical shape and lack of historical documentation prior to 1908 suggested it might actually be a small impact crater. The Lake Cheko hypothesis posits that a fragment of the main asteroid survived the airburst, striking the marshy ground to form the lake. However, this theory remains highly contested. Subsequent analyses of sediment cores from the lakebed indicated the presence of deposits predating the 1908 event. The ghost of Tunguska continued to confound, proving that forensic astronomy in a dynamic, eroding terrestrial environment is an incredibly complex endeavor. The ongoing debate highlights the inherent difficulty of dissecting a transient cosmic event. Unlike the Moon, where craters remain preserved for billions of years, Earth actively erases its scars. Weather, vegetation, and tectonic activity quickly obscure the evidence. The Tunguska event represents a critical threshold in our understanding of these impacts. It sits perfectly at the intersection of a massive energy release and zero macroscopic evidence. This intersection is what makes decoding the blast so vital. Near-Earth object surveys constantly scan the heavens for massive, civilization-ending asteroids, but objects the size of the Tunguska impactor, roughly the size of a large building, are incredibly difficult to detect until they are mere days from collision. There are millions of them in our solar system, and the Siberian wilderness proved exactly what happens when one slips through the net. The study of this event has birthed entirely new disciplines in impact physics. Researchers now run complex hydrodynamic simulations on supercomputers, modeling how different compositions of rock and ice interact with the Earth's atmosphere at hypersonic speeds. Every simulation, every microscopic particle recovered from the peat bogs adds a crucial piece to the puzzle of planetary defense. The devastation of the Podkamennaya-Tunguska River basin stands as a stark monument to the violent, chaotic nature of our universe. It is a reminder that the Earth is not a closed system, safely isolated in the void. We are constantly moving through a cosmic shooting gallery. The blast that flattened 80 million trees fundamentally altered our perception of the sky above us. The mystery that began with a blinding flash and a missing crater has evolved into a rigorous scientific mandate. It forces humanity to look upward with a mixture of awe and vigilant caution. The secrets extracted from the scorched Siberian Earth have equipped us with the knowledge to anticipate the next celestial intruder. The Tunguska event remains the ultimate cosmic vanishing act. An explosion of unimaginable power that left no crater, only a legacy of questions. By meticulously dissecting its absence, we have uncovered profound truths about our fragile place in the solar system. The skies may seem silent, but the flattened forests of 1908 echo a warning we can no longer afford to ignore.